Yeah. Okay. So again, so yeah, sorry for the glitch. So these agendas were copied from the last slide, and it was not updated. I mean, I just updated it in the last moment. So it is understanding the basic neural language model. So that's where we will start the basic neural language model. What is a language model? What is structured prediction and why is it important? And then conditional language models. What is it conditioned to? What does condition mean? Now, using attention to handle information bottleneck problem. So what is an information bottleneck problem in normal or naive RNNs, and what is, how do we fix it? And then self-attention and transformer model. So that is sort of the agenda for this topic. And as always, the resources are from Sergey Levin's CS1W182 course, lecture 11 and 12, and there is a very good, I mean, there are lots of resources for transformer, self-attentions, multi-attentions, etc. Nowadays it has become a sort of hot topic in both language, vision, and even audios. So this particular YouTube channel I like, they have very lucid explanation. So AI Coffee Break with Leticia, and this is the link for the YouTube channel. So I have taken some parts from there also. Okay, so let us go to this basic neural language model, and then again, as it will help me to basically annotate in my tab, I shall switch to tab. Just give me a second again. Okay, so yeah, it's recording. Okay, so the language model basically is a model that assigns probabilities to sequences representing texts. So this is what I mean by this. A language model is a model that assigns probabilities to a sequence representing text. So the idea of language model, I mean, if I just tell from this definition, I mean, it may not be very clear. But what it means is that a language model often is used to generate text. So how does it generate text? So if you think that, okay, text, that is sentence, is a sequence, and it provides probabilities to these sequences or elements of the sequence, then it can, I mean, you can probably sample from these probabilities the most probable sentence, or in other words, the most probable words given the previous words. So, and sometimes given some other conditions, maybe that given an image and given some first initial few sentences, words in the sentences, which are called prompts. So prompts and images, if you give, maybe it will complete the sentence. Because you can then always sample, if you get a probability distribution over all the words in your vocabulary, you can always sample according to that probability, and it will ultimately generate a most likely sentence given those conditions. Okay, so that is the sort of output of a language model, or the idea of using, how can use a language model. So let us go ahead a little. Things will be much more clearer after that. So why are we bothered about language models? Because because we are just discussing say RNNs or sequence to sequence models. So many language models can actually be represented as the following general architecture, which you can from your previous two basically classes, you can understand that this is a RNN. So you give some input as the elements of the sequence, and you are getting these outputs. What I am telling is that these outputs will be the probability distribution over all the words, and you are just taking the maximum probable word, or just sampling according to that probability distribution. So what is the difference between just taking the maximum probable word and sampling according to the probability distribution given say at this instant? The difference is that when you sample, you may not always get the maximum probable word. So it may be with say I mean, the maximum probable word is maybe say 80 with comes with 80% probability, but there are still some small probabilities, say 1%, 2% to other words also. So that can always come, I mean, sometimes come. So there are basically these two ways. And language models so can be represented as this general architecture. So it is more general. We'll go and make it more specific as we go along. Now, so we see that there are basically multiple inputs. I mean, multiple outputs we can understand that, okay, I mean, it's a language generation, that is sentence generation model, say. So this is the first word, this is the second word, third word, and so on. But why do we need multiple this should be input. So there is a typo. So why do we have multiple inputs? So the thing is that, okay, yes, it is possible to just state or give direction to this model that, okay, generate a sentence for me, and only that will be the input, nothing else. But the most problems that require multiple outputs, for example, in our case, just say the text generation or sentence generation, have strong dependencies between these outputs. What do we mean by these strong dependencies between these outputs? It is that, I mean, if you don't let the model know what it has generated earlier, suppose it is trying to generate the third word. So if you don't let it know that, okay, what are the first and second words are, it may not generate a very meaningful sentence. It may be it can give, okay, in all the sentences that you have that you have trained this model using, or the model that you have trained using all the sentences, training sentences, what is the most likely third word in those sentences, collection of sentences. It can just generate that, but that may not mean that, okay, it will be very much relevant to the first two words that has been generated. So that is what we mean by they have strong dependencies between these outputs. So between these outputs is important, and that is why it is sometimes called as structured prediction. So the prediction may not be just independent or individual. They have to be structured. It has to follow the structure. I mean, the example, the basic, I mean, I would say the easiest example is the sentence generation. So it has to follow the grammars of the language. Okay. So that is sort of what we mean by this structured output, and that's why these sort of problems are called structured prediction. So let us go to some more concrete example also. Let's say we have a text generation model which generates text given an initial prompt. So I was saying that the initial input may be the first word or prompt, as I was telling. Let the word of the language model consist of the following three sentences. Let's say that my training data just have these three sentences. So the first sentence is, okay, I think, therefore I am, I like machine learning, and I am not just a neural network. Okay, so these three sentences. Suppose your initial prompt is this I, because yeah, you have this all these sentences say basically starting with I. So I'm just giving a word, initial word I, and I'm just telling that, okay, this language generation system model, that is language model, to generate for me a sentence. Okay. Now suppose suppose it has been trained a good trained good model. I mean, you have this RNN which have shared layers, etc., that we have studied last week. And suppose it has learned that, okay, it is a very good say model, and it has learned that, okay, the probability of the second word basically moves with this this think, like, and am are the three basically options for this second word as the second word before I, after I, and they are almost equally likely. So just 0.3, 0.3, 0.4, which are almost equally likely. So it gives out a probability distribution like this. That is, given this word I, first word I, it says that, okay, there is equal probability of think, like, and am. Okay, almost equal probability. Now you sample it, or the model samples it, and suppose you get this word. So suppose this think it becomes the word that you have sampled at this time step. Now you will basically ask the next word to be generated. So again, if we don't let the model or the this second time step of the model to know that okay, we have sampled this, what will it do? It will do that or it will try to find what are the three possible third words. So it is there for machine and not, and they are also again almost equal probability. So it will just emit this probability that this is the probability distribution or most likely probability distribution of the third word. And if you just say sample it, it happens to be that it comes as this word, because all are sort of mostly equal probability. So now you see it has become that I think machine. Okay, so it's not starting to make sense. And similarly, for the next time step, again, the fourth word is I, learning and just. It can even, I mean, and again, it's emitting these words, these three words. And when you sample from this third time step, suppose it has given you just. So though the model is very good, at least giving probabilities to this first, second, third words, it does not have the structure that okay, it does not obey the structure that okay, I think machine just is not a sensical statement. So output is nonsensical, even though the network did great job individually. So individually at every time step, it is following what it has been learned or it has been taught. That okay, think, like, and am have equal probability as a second word, so it has just emitted that, and you happen to sample think. Similarly for therefore, machine not, and I learning just, and so on. So it has learned this fact, but in a combination, it's not doing a great job, and that's why this structured prediction will come into picture. So we need to say fix this. How to fix this? And the basic idea is that you need to let the model know what the sampled output is. So we will go to that, but I see a question coming from Rishabh, so I am asking him to unmute. Yeah.
I have a small confusion. Like in this case, you mentioned think, like, and MS 0.3, 0.3, 0.4. They sum up to be 1. But so like, but like there are many more words, sir. Like there should be think, therefore, for a single. So I think, sir, there's a small confusion. So there may be like 20 or 27. This sum of words.
Yes.
So
Yes, but
each of them
yeah,
should
I
be
mean,
the probability.
what I mean by this is that whatever is the number of words here, say 20 or something, I don't know. I mean, the number of different words, the vocabulary size. So for all the other things, it's 0. You can think. Okay. So it is not actually giving only 3 length vector. It is giving probability vector whose length is equal to the number of words in vocabulary. Okay. Okay. Kaushik, some question. Yeah, I have asked you to unmute.
Yeah, sir, just a question like maybe we can or can we imagine this more like say each box is an say LSTM cell with your output more like coming from the hidden state and the right hand side output coming from the cell state. So if we do that, and I guess you are then the difference is that you are sampling think. You are doing that sampling operation on the hidden state,
On the output.
but on the output,
Mhm.
yes, on the output, but you are not letting the
I think I have dropped
you
you.
know right because
Sorry.
what I'm thinking is that both the right hand and the
Maybe
top arrow will kind of carry
once.
the same information.
Yeah, maybe I lost for the last 15-20 seconds.
Oh, I'm sorry.
Yeah. So you said, I mean, what I last heard is that we are sampling from the output. Then.
Yes, sir. So we are sampling from the output. Say for the first one we got is think.
Mhm.
and the information or the output that is carried is think 0.3, like 0.3, and am 0.4.
Right.
And then on the right hand side arrow, similar information is expected to be carried, uh, given you have just started and your cell state and hidden state are kind of the same.
Mhm. Mhm.
So the difference between the top arrow and the right hand side arrow, is it because on the top you are sampling it, but on the right hand side you are not sampling, you are passing all the information, I mean all the probabilities.
Yes, yes. I think I'm getting your question. So you are saying sort of in a way that the same cell state or same hidden state is generating this probability, and you are also passing it to this. So how can you
Right.
say that this does not know,
Yes sir, yes sir,
right?
kind of, yeah.
Yeah, and
Yes, yes
yeah,
sir.
kind of. And what you said is right. That yes, what does it know? It knows that this cell state is responsible. I mean, this, what does this right hand side know? That this cell state is responsible for giving a probability distribution. But what you are sampling explicitly, that it does not. And that is what is the missing link, sort of say. That if we can just put that information, that okay, not only that this is the probability distribution, but what I have sampled, that will fix the problem. Okay, does it answer
Yes,
your question?
yes,
Yeah, it will be more
yes
in
sir,
the
it does.
next slide itself. Yeah.
Absolutely it does. Thank you sir.
Okay, so let us go ahead. And this is the exactly the thing that I was telling in response to Kaushik's question. So fix is fit sampled output. So the important thing is the sampled output as input to the next step. So the network previously was knowing that, okay, the first probability distribution, the first output probability distribution is this, but it did not know that it has sampled. I mean, our model has sampled this as the output, right? I mean, ultimately, for any practical system, if you just give the probability distribution as output, it will not work. You have to give one single word, and that's why you need to sample. And that sampled word think you are giving here. So now the network knows it is predicting the third word of a sentence where the first two words are I think. Initially, it was, I mean, in the first case, what it was doing, or what the network was sort of knowing that, okay, it is generating the third word where the first word is I and the second word's probability distribution is this, right? So that is the difference here. It knows the first two words definitively I and think. So it will basically do its calculation, and then it will give more probability to therefore, because if the first two words are I think, then of course therefore has more probability, because there is not like I think in other two sentences. I mean, it's of course more sentences are there for training, but yeah, again, for our contrived example, we are just thinking about these three sentences. So it is giving, okay, I think this slide I was on. Yeah, this is giving this therefore more probability. So when you sample it, it has more chance of sampling this therefore. So this is next time. So you will basically pass this therefore to here. That is what is done. So now the network, yeah, so that then it will give more probability to the next word I. So if you are outputting I think therefore, then the fourth word would be most likely I. Suppose it was the first word was sorry, the second word, sampled word was like, then it may be that, okay, I like, then machine would have gotten the most probability. And once you sample it, at this time, when it is generating this word, fourth word, the sentence that is already generated is I like machine. So maybe the most probable word next, the fourth word will be learning, and so on. Okay, so that is the simple fix, and this has a particular name. Yeah, this is the name. So this is known as autoregressive model. So it's sort of regressing its output Again, this name stuck for historical reasons. I mean, with the time series data, people have used these models, sort of not say RNNs, but other sequence to sequence models, say HMMs, that is hidden Markov models and so on. But from that time, this name stuck, that is, it is an autoregressive model. And the key idea is past outputs should influence the future outputs. So future outputs were not getting influenced by the past output earlier, but now your past outputs should influence the future output. So this is also known as the autoregressive model. Yeah, so what will you require for training such data, such model? The training data is input is the sequence and output is the same sequence offset by 1. So the input is, say, I mean, when you are giving, of course, you have to give an input and output. So if I tell them as pair, so input output pair, the input will be, say, I think, therefore I am, and the output will be think, therefore I am, stop. So some sort of notation to use the stop. So corresponding to I, the output will be think, then corresponding to think, it will be therefore, and so on, right? So that way you basically, I mean, this is the input and this is the output, and it goes on. And ultimately you have to provide a stop token that will be coming in a few slides, and it will know, the model will know that it has to stop generation when it generates that token. Okay, now one question maybe, yeah, so that if you basically say your sampling does not, suppose it is I think, that is the first two words are I think, but the third word, suppose it comes as machine. So there are ways to basically train in this, to basically tackle this sort of discrepancies in sentences, I would say. I mean, discrepancies, it is not discrepancies, but I mean, it can give in 10% of the time, say this word machine, but can it then correct it? Say, I think, therefore I am is what you want. Let's say it generated I think machine, then should it generate I am or something, some gibberish? So that also has some way to basically tackle, but we are not going into detail of it. But you can go to this, I think, lecture 10 last part of Sergey Levin's, or no, it's lecture 11 first part of Sergey Levin's lecture, where there is something called scheduled sampling and so on, that you can basically have a look into. Okay, so this is sort of the basic neural language model. There are some few details. Let me start discussing them, and then I'll stop after discussing one or two more slides. So this was basically the, say, the training corpus, so to say, the input training sentences. Now, how do we represent these training sequences? Because you are not going to give these words as the input. So some mathematical representation is needed. And one simple way is basically the way that we have earlier seen in case of classification using neural networks or ConNets. So how do we represent the labels, the one-hot vectors, right? So this is sort of the similar idea. One thing is that, okay, tokenize the sentence. So what does it mean by the word tokenize or token? So each word is actually called a token, and we use this one-hot vector representation. So what this length of the vector is the number of words in the vocabulary. Okay, so if you're say first, what you will do is you will probably split all these sentences into words, and then you will see what are the number of unique words. There are other things also for practical purposes. There may be spelling mistakes, etc. There may be very, I mean, that can be probably you can sort of get an idea that, okay, this is spelling mistake. If, say, in the whole vocabulary, suppose it has 10,000 sentences, and each, say, on average has 10 words. So among the 1 lakh words, I mean, 1 or 2 words has frequency 1 or 2 maybe. So those are, I mean, generally discarded. I mean, those are sort of outliers that you can think. Mostly it has been seen that these are the typos and spelling mistakes, etc. So, but there are other practical issues also nowadays, like the smileys, etc. Those different sort of shortened version of the words, they also come. But yeah, that makes it a more challenging thing. But yeah, let us not bother about all these things. Let's say that we have a very clean vocabulary, and suppose it has, as I said, 1 lakh words. So it will be a, sorry, 1 lakh word, but let's say the number of unique words, maybe say 5,000. So these 5,000 will be the length of these words. I mean, length of this vector, one hot vector, and you will sort of say arrange these 5,000 words in some order, right? In the vocabulary. It may be in alphanumeric order, but it can be any order. But once the order is fixed, that is the position of each word is fixed, you cannot change it. And then suppose you are trying to represent this first word I, then you will just pick the corresponding index of the letter I, and you will put 1 there. Everything else will be 0 in this 5,000 length vector. So that is the sort of tokenization followed by one hot vector representation. There, and you do it for all the words, and I mean, when you are giving input, you are just giving these as input. Okay. More complex are word embeddings, which takes care of the fact that, okay, there are words which are say similar in meaning. So those words representations should be closer. I mean, let's say just that, okay, I mean, king and queen, they are pretty much very similar thing. I mean, it both say relate to say royal thing. So if king's representation is something like, say, suppose your vocabulary is 5 words, so this and this, then the queen may not be very very different. I mean, though it is if you just put the king's index here and queen's index here, still, I mean, the similarity between them, if you just think about the L2 norm, it is basically 0. I mean, the distance is sort of high. You just take the difference and take the L2 norm, right? So it should not be that. It may be that, okay, if this is 0.8 say, and this is say 0.2, maybe this is say 0.7 and this is say 0.3, something like that. And that means that the words that are closer in meaning, they should be closer in the representation space. So when I said 5,000 word vector, that means it's a 5,000 dimensional space. Here it's a 5-dimensional space. So each representation is a point in that space. So these, I mean, the point representing king and the point representing queen, they should be closer. So that's the idea of word embeddings. We will look into it maybe next week, how to learn these word embeddings and so on. But yeah, as I said, we will cover this later. But these are more complex ways. But the simple also representation also works pretty good in practice. Okay, I see still a raised hand from Kaushik. I mean, is it from the previous part, or I mean, you can then unraise, or I can ask you to unmute. Okay. Okay, some more details. So how does the model know it has to stop generating words? So I sort of briefly mentioned about this stop token. So that is the use here. So during training, add a special token. Just I'm calling that this word is this EOS at the end of the sequence. It may be that it's a sort of the last word in the vocabulary. So if you have a total 5,000 unique words, now your vocabulary is 5,001, and this 5,000 first position is sort of reserved for this end of sequence. You can think of it as the representation of, say, the full stop. Okay, so during training, add a special token end of sentence at the end of the sequence. During testing, when it produces this, that is, when it produces a high probability for this 5,001 5,000 first position, we know that the sentence is complete. We will not generate it more again. So this is the last word it has generated, EOS, the end of sequence token. So we will not generate it. Okay. Now, similarly, a special start token is introduced to kick off the start of a sentence. I mean, you can always just sample the probability of all the first word of the, I mean, you can just find the, say, the frequency distribution of all the first words of the, or sort of all, yeah, the first words of all the sentences. And from that probability distribution, you can, say, sample one word, and that will kick off your, that can kick off your sentence generation process. That is, this I, you just sample according to the frequency distribution of the first words in your sort of corpus. But this is a more elegant way. I mean, it basically makes things uniform, that okay, you have this, everything is dependent on these tokens. You don't have to sample. It will just do its own job. I mean, the model will own job. I mean, your task will be to just feed this start token, and it will start generating whatever it likes. Okay. So this is some few details. Okay. So before I go to conditional language models, if there is any questions, please raise your hand. Yeah, Rishabh, let me ask you to unmute. Yeah.
So like in this case, when we are reading a start token, sir, if you want to, like, if suppose we have generated 2 sentences, sir. But so like, if I have generated like some sentence, I like machine learning, and it is the highest probable sentence. Then after n token, it will again restart something like I want to generate 2 sentences, but it will again generate that. So with using the start token, I'm generating the same 2 sentences.
No, it may not generate the same sentence, because if your corpus is, say, 10,000 words, 10,000 sentences, and your say 9,500 sentences are starting with I, then only it will start always with I. Or if your say 9,500 sentences are say the same sentence, I think, therefore I am, then only it will always generate the same sentence. So what I mean by this is that if you have a very diverse corpus, it will not be the case, because the first word itself will have a very sort of uniform probability. Okay, so if you look into the normal corpuses, you will of course try to make your model as diverse as possible. So unless you give this skewed or imbalanced data, it will do a good job.
So it also depends on the, like, which word is highest probable, because after start it will come up to the word that is most probable in the corpus. Like
Yes,
if I
not only the corpus, the first word of the for the first word, it is the first word of the corpus, or first word of all the sentences. For the second word, then it becomes this dependent on the prompt, that okay, what is the probability that given this first word, what is the probability of second? For the third, given these 2 words as the first and second, what is the probability of the third word, and so on. Okay.
So sir, like, can I say it's like summary detection of some text, similar to, like, means we are training.
That is a different problem. That's a different problem. Summary, getting summary is different problem. I mean, you will have, say, a long paragraph, and from there you want to get the summaries. For that, the data is different. I mean, the training data is different. You have to give the summary and so on. It is just generation of sentence. Okay. Okay. Yeah, you can unraise your hand. Let me go to the next part. So as I said, it is just generation. So what we mean by this is that we have seen this unconditioned generation. So we are not saying, okay, which sentence to generate. I mean, is it just randomly generating sentences from the corpus? So that sort of question gives rise to this these next models. It is conditional language models. Text is generated conditioned on some input, and that input can be different things. For example, one input can be image caption. So you are conditioning your generation of the sentence on the input image. That is, you are basically giving the image as the input, and you are saying, asking the model, that can you tell me what is going on in the image? So conditioned on the image, what sentence it will generate. So for that, you get this, I mean, you start with this language model, the basic language model that we are discussing from the time being. But for this basic language model, you see that we had earlier started with this start token, and you can think, I mean, when we discussed the RNN for the first time, that okay, we are actually feeding or the sort of the initial hidden state is all zero. The hidden state here is H1, which is not all zero, or this is H2, it is not all zero. But here it is H0 is zero. So just keep that in mind, and we'll see what are the changes that is incurred here. So previously the state of RNN was zero. So two important things to notice. One is this that I just told, and another is you are starting with this start token. Now, this image captioning, what you are doing is that you are giving an input image, which I am telling as say xi. Now, we set the initial state of the RNN as the encoded representation from the image. Of course, as you have encoded the input words, you have to give some sort of a mathematical representation summarizing sort of this image, or what is going on, encoded, sort of an encoded representation, basically a mathematical representation of the image. So we have seen that convnets can basically represent an image very good. So we can just give a convnet, but you can also use your handcrafted features. Earlier people have used it, but nowadays, of course, conv features are more powerful, strong, so they use conv features. But you can use those the features that we have mentioned briefly. These say the histogram of oriented gradients, hog, etc., sift, etc. But anyway, you pass it through a convnet, and of course not you don't take the last layer output, that is the classification output, but somewhere in between, maybe the last conv layer, even the third conv layer, even the first the fully connected layer, if it has fully connected layers. From somewhere it from that convnet you are taking that encoded representation of the image. So now we set the initial state of the RNN as the encoded representation from the image obtained by passing it to the convnet. Now, and then both RNN and convnet are trained into it. So this H0 now is basically fxi. F is just this function, this convnet. So you pass xi through f, you get fxi, and that you feed as your initial hidden state representation of the RNN. And then you do the similar thing, that okay, you are giving this start token, but it is now conditioned not on zero, but this image. It is generating say a, then you are feeding, of course, here this a, that is denoted by this a, cute puppy, and so on. Then end of sentence token it is generated. And both can be trained end to end. So you just give this paired data, that is this image and the corresponding caption, and then you backpropagate through it. And it is, I mean, RNNs, we have seen how to backpropagate through it, and convnets also we know. So it can be trained. So this is the basic idea. So CNN encoder summarizes what is going on in the image, sort of, and RNN decoder expresses the content of the image in words. So the role of the CNN encoder is that what is going on, what description I want that from that image, that it sort of gives as input to the decoder. So this is called CNN encoder, and this is called decoder. So it is encoding the information content in the image, and it is decoding that encoded information in terms of natural language texts. So this is also called an encoder decoder architecture, and we'll see a lot of such architectures in the subsequent lectures. Yeah, so training data is, as I said, paired image text data. So paired means the corresponding, so the image and the corresponding captions. So it may have several captions also. I think in when I described about the COCO data set in detection and segmentation, COCO is a data set which is used for image captioning also. And I said that there are 5 sentences or descriptions per image that has been collected from users. Yeah, then it is not that only images can condition the language model. The RNN decoder can also be conditions on another sequence, say text from another language. So it is not that only the encoder encodes the image. It can actually encode, say, a sentence from another language. So as the example says, it is say the French sentence for this acute puppy, which is something like anchi or mignon, something like that. So, and text from that, yeah. So the first RNN reads in French. So it a very similar sort of architecture. So it is decoder, it is encoder, but both are RNN or LSTM. So you are giving the start token. I mean, you may not give it, but yeah, I mean, in sort of training, you will give it. You are giving. So this start, then it's just telling the model that okay, we are going to start the sentence. It's not sampling, because you see there is no output here. So you are not getting the output and feeding. You are just giving your training sentence. So these first 3 words are given, and then you are telling the decoder, and sort of you are feeding this I mean this I mean, if I just call this as FXI, the encoded representation of the French sentence, that is fed to as the first time at the first time step of this decoder, and it basically does the same thing. So yeah, so the first RNN reads in French, produces H0, and the second RNN takes H0 and produces English text. The encoder is also RNN based. So previously the encoder was, previously means for image captioning, the encoder was CONVNet, and here the encoder is also RNN. Both are RNN. Yeah. Okay. So one thing to notice is that this H0 is only virtual. So you can actually think that there is nothing in between. So I mean this thing. So whatever is the output from this time step, it directly goes to there as to the start of this sentence, sort of English sentence. So this end of sentence token in French doubles as start token in English. So after this, there is a end of sentence token, which can be thought of as the same as this start token in English. I mean, these are some few details, I mean, that you basically do, I mean, give as, I mean, sort of take care when you are implementing it. So the start tokens position in, say, one hot vector representation in English, and the end tokens position in French, they can be same. So yeah, start token in English. And another important thing is that the same RNN also you can use, because there is nothing in between which is different. So you can just make that, okay, these time steps, they all share the weights, the same weights. Okay, because it's just after it generates the end of sentence, or after it sees, not generates, sees the end of sentence token in French, it basically just starts generating this English sentence. So it is not that I mean, nothing is stopping you to share the weights between these two, this encoder and the decoder. The thing is that practically people use different weights for these two parts. So these are still shared. I mean, this is shared and this is shared, but different set. So this is one set of shared weights and this is one set of shared weights. That sort of practically people use. So that, I mean, intuitively you can think that, okay, these weights have learned, these weights have to learn to generate sentences, and this does not. So maybe it will help if you can just sort of demarcate between them. Okay, so these are some few details. Again, some more few details. Yeah, sometimes the encoder RNN reads the source language sentence in reverse. So this is the first, this is the second, and this is the third. And the idea is that, okay, the first sentence or the start word in the target language, which is English here, may have more dependence or more relevance to the start word of in the source sentence, which is French. So that's why it is just a way to basically bring them closer. But that also sort of gives rise to this question that, okay, then this last word and this last word, they are more further apart. So will that be problematic? In practice, it has been seen that this slightly gives some advantage. Performance wise, empirically it was validated, but not much. I mean, you can very well use that. But since it does not change anything in terms of, say, computation or inference time, whatever is giving slight improvement, you can use. Again, this I told, typically 2 separate RNNs are used, but you can use a single RNN also. By single RNN, we mean the single shared weight, and 2 separate RNN means with different weights. Both the RNNs are trained end-to-end on paired data, that is pairs of French and English sentences. So both these RNNs are trained end-to-end on this paired data. So this is, I think, okay, yeah, this is probably the last slide before I stop. So RNNs can also be stacked. Each RNN layer can use LSTM or GRUs. I mean, it does not mean that RNN is just naive RNN. You can use LSTM cells or GRUs. I mean, these can very well be just the LSTM or the GRUs. And stacked means we have not, I mean, by stacking, you can increase the depth. So as we have seen in case of, say, ConvNets, increasing depth helps. For example, VGG is a very deep network compared to, say, AlexNet. So you can also use, say, a depth of 2 here. So it is not just that you are getting output from here. You are feeding it as an input to the next layer of the RNN. This output is in turn fed as the next layer of RNN, and then it is we are taking the output from the last layer, and so on. So this is basically the stacked RNN architecture, which can also be used. I think I will stop here for a bit. I mean, maybe I'll just start this thing 1 or 2 slides for tomorrow. But if there is any question, you may please proceed. It will take me like 2-3 more minutes. Okay, if not, then quickly let us get started for tomorrow's lecture. Maybe just 1 or 2 slides, I'll go ahead. So as I said, the second agenda was to discuss the bottleneck problem and how to sort of tackle the bottleneck problem. So we have seen that the information, I mean, this is the basically the architecture. I have just made them different colors, the encoder and decoder. So to basically emphasize the fact that they are just separate RNNs, but shared among their type steps, the weights. Now, all the information about the source sequence is contained only in the activation at the beginning of the decoding. So you have summarized this French sentence at the end of this RNN, and you are feeding it to this. So whatever, I mean, if it is even if it is a long sentence, whatever are there, different clauses, maybe different subjects, different objects, what are they doing, and so on, all thing needs to be contained at this one long vector, which is coming as an output at the not output, sort of the hidden state at the last layer, right? Last layer of last time step. So all information about the source sequence is contained only in the activation at the beginning of the decoding, which is fed to the beginning of the decoding. Entire decoding is based on the initial information. So I mean, this decoder does not have a chance, does not get a chance to revisit what was there. Maybe that, okay, it has forgot. It is trying to generate, okay, what is following on. But this representation was not giving it. So it would help if it can revisit. So that is not happening here, and that is the bottleneck, that everything is sort of summarized here. Okay, so for long and complex sequences, it will help if the decoder can peek into the input sequence time and again during decoding. So when decoding this, it would help if it can see again this part, maybe some of the relevant parts, this one, maybe again, because when it is generating this sentence in normal, what we have seen in the basic neural language model, it depends on this summary and whatever it has been converted through by passing through this time step. Okay, so but it will certainly help it if it can peek into the input sequence time and again during decoding. Yeah, how can we do this? So let us stop at this point and we will see how can we do this starting tomorrow. Any questions in today's lecture? Okay, if not, then again, yeah, I mean, I'll end the meeting, but before that, just reminding you that this Friday, instead of this Friday, I will take the class on Saturday 3 p.m. So not Friday 8 a.m., but Saturday 3 p.m. This Friday. Okay, and about the exams, you will probably know from the institute, as we will know. I can also convey.